We are now at week 11. Today we will have a short lecture on transverse stress distribution and torsion of circular bars. So, as I said, we are at week 11, so that means that we're getting close to the end. This is the semester schedule, so we will only, after this week, we will only have 2 weeks left, where we will mainly work on examples. This is also reflected in the learning objectives, seeing that we are now, with today's material, we are covering the last 2 learning objectives of the course. So, specifically, point 9, to be able to calculate stresses and deformations in torsion of round bars, and also final learning objective to determine shear stresses throughout cross sections of beams. So, shear stresses in beams. Well, you can actually say that this is the missing point. We have looked a lot on normal stresses in beams, and the motivation for doing so has been quite clear that the normal stresses are usually the ones that are the most important. That gives rise to the biggest stresses in beams, and therefore they could argue that they are the most important to look at. But to get the complete picture, of course, and to get a more accurate assessment of the magnitude of the stresses in beams, of course, which is important because we want to know if the stresses are so high that we will have failure or yielding of our material, we need also to be able to take the shear stresses into account. So just to recapitulate a little bit, let's go just looking at the stress resultants. This is old material, so remember that when we look at the stress resultants, which I have drawn here by making a cut in a beam, remember we have the bending moment that we call M, we have the normal force that we call N, and we have the shear force that we call V. So the corresponding stresses, as I said, we haven't really been looking at the transverse stresses yet. So the transverse stresses are the stresses that come from the shear force. We have looked a lot on the normal stresses coming from the bending moment and the normal forces coming from the normal force. So when we have a normal force, we get a constant distribution of normal stresses at our cross section. And of course the integral of these normal forces, the sum integrated over the area, gives rise to the normal force that we experience. For the bending moment, we have seen that a bending moment also gives rise to normal forces. However, they will vary in a linear fashion over the cross section. Like this. Of course, this is the case only when we have the centroid in the middle of the beam, and things of course get more complicated when we have composites, as we have seen the last few weeks. But this is the standard case of normal forces and bending moment and the corresponding normal stresses throughout the cross section. Now, the question that we will just address today is, let us call it the shear force. So, what will happen and what are the stresses that corresponds to a shear force? So let me just, for completeness, this was the normal force, this was the moment, and this is then the shear force. So what will the stresses look like? Of course, the stresses will in some fashion be distributed along the cross section, but the question is now, how are they distributed? So let's go back. Well, so there are actually 2 approaches to this. One is the very simplified version, which is not very accurate, but which is used sometimes to get sort of a qualitative and a very approximative assessment of the magnitude of the shear stresses. And that is to assume that they will be constant, just as if we had a normal force. So this is what we just looked at for the normal force. This is just what we looked at for the normal force, where we had a constant stress distribution that gave rise to the normal force. And the first approximation to the shear stresses or the transverse stresses is that we have the same phenomenon going on for the shear stresses, so that we have a constant distribution of the shear stress along the cross section. So the magnitude of the shear stresses for that approximation is, of course, then that we just find the magnitude by having the shear force and divide by the cross-sectional area. In reality, however, that is not the case. So specifically, by looking at more advanced equilibrium conditions, we can see that at the top of the let me just erase this one. At the top of our cross-section, here and here, if we look at advanced equilibrium conditions, we can actually see that we cannot have transverse stresses at those points, because it has to be in equilibrium with the stresses on the top of the beam, and there we do not have any stresses, so they must also vanish very near the cross-section top and bottom points. So in practice, we can see that when we do solve in a more advanced way, we can see that the real distribution is more in the form of a parabolic stress distribution like this. So this we can express with the equations that we have stated over here. So here we have instead a distribution of transverse stresses, that is a tau, which is the transverse stress, as a function of z equals the shear force, and then we have the distribution function. We have the moment of inertia, and we have the width of the cross-section. And the distribution, we can see it's written down here, which is indeed in the form of a parabolic distribution or parabolic function here. So this one, for simplicity, to get a rough estimate of the magnitude of the shear stresses. If we want more detailed assessment, then we go for the more complex function where we have the parabolic shape. But that's actually all we're going to do to look at the shear stresses. As I mentioned, the normal stresses are usually much more important, and then we may just use the very simplified rough assessment to get the additional stress that we get from the shear forces. Okay, so that was the first topic of today, very shortly covered, but we're also not going to do really exercises in terms of transverse stresses in beams. But what we are going to work on a lot today is torsion of circular beams, which is also going to give rise to transverse stresses. Now, when we look at a very general three-dimensional problem, so we see here up here in the top left corner, we see a beam structure subjected to a three-dimensional force F acting at the corner point here. Now let's see what kind of forces and moment that actually gives rise to. So we haven't looked at such a general force before in the three-dimensional case. Well, maybe in the beginning in terms of statics, but not in terms of the stress resultants that gives rise to. Now, in a two-step procedure, we see first that we can resolve the force F in the three components, Fx, Fy, Fz, acting in the corner where we have the load acting as well. But with the aid of some of the results that we already covered in the first weeks, where we can see the equivalent force system, we can actually move that force system into the centroid C, and then add a few moments to get the equivalent force system. So in total, we end up with three forces, again, put in the centroid. So these are the Fx, Fy, and Fz forces, but these are the same as we saw up here. But then we have the additional moments My, mz and mx added because we have moved the force system into the centroid. Now let's take a little bit more detailed look in these moments and these forces. So if we look at what we have been covering so far, looking at the beam structure up in figure A, then we can see that the Fz is actually what we have been looking at so far as the shear force, right? Fy is also a shear force, but that's in the other direction. So that is, if we turned the beam upside down, rotated at 90 degrees, then that would be the shear force. It's just the shear force in the y direction instead of in the z direction. Now, our my, that is actually the bending moment. The traditional bending moment that we've been looking at so far. And similarly, our mz is also a bending moment, but in the other direction. Our fx, if we look at the the figure to the bottom right here, that is our normal force, our fx. Now all that's missing now is the mx. So what we can think of mx is like it's trying to rotate the whole object. So it's what we call a twisting moment. And when we apply a twisting moment to our structure, we get torsion. Right. So it's this moment that we're actually going to focus on in the coming slides. So this is the torsional moment that comes from the fact that we have a force acting on our structure in an eccentric way. So it's the first time we've been looking at such a load on our structure. So a twisting moment giving rise to torsion of our structure. Now looking at torsion on rectangular cross sections, it's not that easy. So we will focus on circular rods or shafts. And we will still have this the torsion moment, what we call mx here. Now let's see what happens when we apply a twisting moment to our circular shaft. Well, if we look at the figure to the right, we can see that we of course get the twisting of our circular cross section, and we will make a few definitions here. So our gamma is what we call the shear strain. We will define that as the shear strain. And then we have the twisting angle that we call theta. So this is not, it's theta here. Okay, so when we look at the geometrical connection between the twisting angle and the shear strain, we can set that up using the first conditions that we have put up as the shear strain condition, that gamma multiplied by dx. Well, we have gamma here, and we have dx as the length of the section that we have drawn. So the product of these two gives the arc length that we have here. But that arc length we can also compute by the twisting angle, d theta multiplied by the radius r. So putting that together, we get the following connection between the shear strain and the twisting angle for this short section dx. Now, the Hooke's law for twisting or for shear we have already covered in one of the previous slides or one of the previous lectures. And here we have the torsional stiffness G. That we use to relate the shear strain and the shear stresses. So now inserting the relation for the twisting angle, we then get the following connection between the shear stresses and the twisting angle. Here. Now we can go on a little bit by relating now the shear stresses that we get from the shear strains and relate that to the applied twisting angle. So now we use the simple mt to indicate that it's a twisting moment instead of using mx. Now, of course, obtaining the moment from the stresses, we need to integrate over the cross-sectional area, and we multiply the stresses at a given point with the corresponding radius that it applies in. And by doing that integration, we get an expression for the moment contribution. Now we insert the expressions from the previous slide And then we can see that we get a characteristic quantity, which looks very much like the moment of inertia that we covered earlier. However, the integration here is done over the r, that is the radius, and not x and y. And that means that it actually gives a little bit different expression. And we call this integral the polar moment of inertia, or the torsional moment of inertia. And when we want to look it up, well, we can use the same table as for the other moments of inertia. It's in the same table. So look for the IP or IT moment of inertia that we use with torsion here. Okay, so now we are ready to complete our formulas. We can see now that a characteristic product that appears in our calculations is the product between the torsional stiffness G and the polar moment of inertia IT. So we call that the torsional rigidity. And you should of course see that in parallel to what we have already as the bending stiffness, which was E multiplied by I, or we also had the axial rigidity, which was E multiplied by the cross-sectional area A. But for torsion, the relevant quantity is GI, torsional rigidity. And now we can put everything together and see that if we now want to express the shear stress from the moment, we can now find the following expression, that the shear stress will be, we can see that it will be a function of the radius, and it will be computed as the moment divided by the polar moment of inertia multiplied by the radius. So we can see a short drawing here to the right of how the shear stresses are distributed along the cross section. So in the center, shown here and here, we can see we have r equal to 0. At 0 radius, we have no shear stresses, but then the shear stress magnitude will grow as the radius increases, and we will have the maximum shear stress at the outer fibers close to the outer radius of our circular cross section. The final thing that we can now do is actually, from the moment and from the quantities that we have computed, we can now find out what is the final twisting angle that we get out when we apply a certain moment. And putting the expressions together, we get this connection, which we can then integrate to find the final theta, that is the final twisting angle at the end of our rod. This is the general formula that we get here, but often, of course, we have a homogeneous material, so we'll have a homogeneous torsional rigidity. That means we can simplify the integral a lot, and we get this very simple formula for predicting the twisting angle theta. When we apply a certain moment, mt, we have a certain length of our rod, L, and then we have a certain torsional rigidity, G multiplied by IT. Now this is actually all we need to do the exercises that we will do in torsion. We will do an example here, and you will do a similar one in the problem session. I should mention that when we look at torsion, it's actually not the torsion itself that's the problem. It's usually the effect on the rest of the structure that is the main difficulty, and we will show that specifically with this problem. Okay, so the problem that we are trying to solve is a problem of a circular rod that goes from point A to point B, and then to which is attached a handle that goes from point B to point C. And then at the end of the handle, at point C, we have a vertical force acting upwards. So the question we're trying to resolve here is, what is the vertical deflection of point C? And there are several parts to this, and we will take it one step at a time. So, as I mentioned, the torsion part of this exercise, we will get back to it, but it's not the main problem, the torsion itself, but it's the effect on the other parts of the problem. So let's take it step by step. So we will find the vertical reflection of point C. Now, if we first look at beam BC, so that's the handle part of it. Now, if we assume that this torsion, or the rod from A to B, is infinitely stiff, cannot bend, cannot rotate, then this is what we have, of course. Then we have bending of the handle itself. There will be bending of the handle. It might be stiff, but we still have the bending relevant to give a vertical deflection. So let's look at this part isolated first. So bending of the handle. Now, this is a standard case that we have looked at quite a lot of times before. It's a simple beam. It has a homogeneous cross-section, a homogeneous distribution, so we can use the elementary cases. And when we look, then we can see that we have to use elementary case 6, which will predict what is the vertical deflection of our beam. Now, looking at our elementary case, we can see that the vertical deflection that we will call BC at point C, so this is point B, this is point C over here, from elementary case 6 is the magnitude of the force multiplied by the length cubed divided by 3 times and then the bending stiffness here. Now, of course, we need to find the bending stiffness of the handle. And as we see, let's go back a little bit, we see that the height is denoted 2r. It's the same height as the diameter of the circular rod from A to B. And then we have specified that the width, or the in-depth width, is r divided by 2. So these are the dimensions that are given in the exercise, and based on that, we can compute the moment of inertia. So our moment of inertia is 1/12, and then the width, which was r divided by 2, and then the height, which is 2r cubed. And summed up, that gives 1/3 r to the power of 4. Now, inserting that into our formula, we get the final value of f b to the power of 3 divided by e r to the power of 4. So, this is the isolated effect of the bending of the handle. But of course we will have additional effects, because we will also have that the circular part of our structure is affected by forces. And if we look at the circular rod from A to B, well, the first thing that will happen to it is that it will also be affected by a force, hence it will bend. So what is the force affecting our circular rod here? Well, let's look at some statics. So if we have the handle here, let's see if I can make a reasonable drawing of the handle. Here, now we have the shear force. Now, if we look at statics here, just from the handle, then of course we can see at this point here, over here, we will also have a shear force to maintain equilibrium. But we will also have a moment, and that we will see later. But for now, we just concentrate on the shear force. And that's, of course, the force that will be transferred to our circular rod as an upwards pointing force F here. So, the force F will also affect our circular rod AB in the same way as it affected our handle from B to C. So we will also have bending of AB in the same way that we just had bending of BC. So here the length is given as, let's just see here. So the length is A of our circular rod. It's given from the dimensions of the drawing here. A here. So again, we use the elementary case 6. And we will have delta, what we call AB. In this case, we have F, and then the length is A to the power of 3, divided again by 3EI. And this time we have a circular cross-section, and that means that our moment of inertia will be 1 over 4 pi I r to the power of 4. Inserting that, we will finally get 4 FA to the power of 3 divided by 3 pi E r to the power of 4. So that was already 2 contributions. Now we have the vertical displacement of point B due to the bending of AB. We also have the vertical displacement of point C due to the bending of BC. But there's one part missing, and that is of course the torsion. We haven't at all talked about torsion yet. So let's see how torsion will affect this problem. And in order to compute torsion, we of course have to get the twisting moment. So let's see how the twisting moment arises. And we can actually, as I said, look a little bit more on statics on the handle. So we already transferred the shear force F into the shear force at point B. But in order to have equilibrium of the handle, we can see that the force acting at point C also gives rise to a moment at point B. Now the moment, to get equilibrium, now we will use this 3-dimensional drawing of our moment, which is very handy when we do 3D with the double arrows. So when we do equilibrium here for our handle, we see that in order to maintain equilibrium of our handle, then we need a bending moment that actually goes like this. That will create equilibrium of our force F acting at point C if it has the magnitude F times B, right? The B is the length of the handle. The force is F. So to have equilibrium, we will have to have a bending moment in point B of the magnitude F times B. But now see, inside point B, to have equilibrium, and we use the Newton's third law, that actually also gives an equivalent moment on the circular rod of the same magnitude. And if we look at that, we can actually see that the action of this moment is actually in the form of a torsion on the circular rod AB. Now let's go back and look a little bit more on that. So it's a little bit confusing. So we see that this is a bending moment. So it's a bending moment on on the handle BC, but it's actually a torsional moment on the rod AB. And that's because these two parts of the structure, AB and BC, they're sitting perpendicular to each other. So what's a bending moment in one of the beams can become a torsional moment on the other beam. And that's very easily, or most easily seen when we use the double arrow technique to draw the moments, right? So if we had done a 2D version of the force equilibrium on the handle, then it had looked like this. This we have transferred into the double arrow notation here, and then we can see we can directly transfer this double arrow to the other cross section on the circular rod. Now once we have the torsional moment M, we can call it torsional moment here, then it's very easy to get the twisting angle. Because that was the final formula that we just derived in the theory. So the twisting angle at the end of our rod is simply given as mt multiplied by the length, which is a, and then we have g and the polar moment of inertia. So of course we need the polar moment of inertia for a circular cross section. We can look it up, and it's 1/2 pi r to the power of 4, or exactly twice the bending moment of inertia for the same cross section. Now inserting this, we finally get that the twisting angle 2 times F multiplied by A multiplied by B divided by pi G R to the power of 4. Okay, so what is now the effect of this twisting angle? Well, since it rotates the circular rod AB, it also gives rise to a whole rotation of the whole structure, which in turn leads to a vertical deflection of point C. We can try to look at it in the complete picture here to see the total deflection of point C. Now it's a little bit hard maybe to get a grasp of this picture, but first, let's see. This is the isolated deflection. Now everything is pointing upwards, so this is actually drawn upside down, which was a mistake. But, well, now we just assume that everything is pointing downwards. We could just flip it upside down. Now, let's take a look at delta BC. That was the isolated bending of the beam of the handle, right? But we also have a contribution from the fact that our point B is rotating due to the torsion. Now, this was the torsion angle that we get, and that gives rise to a rotation of point B, which in turn moves the whole handle, or rotates the whole handle, and then we get the corresponding deflection at the end point as the rotating angle, theta B, multiplied by the length. So this is this contribution. And then we also have the vertical bending of our circular rod section AB. So the total deflection is the sum of all these contributions, where the second one is probably the one that's a little bit hard to understand, that we have the rotation and a rigid body contribution from the handle that gives rise to an additional vertical deflection. And then we have delta BC here. So putting all these quantities together, we finally get, it was 4 FA divided by FA to the power of 3 pi E R4 plus 2 FA B squared divided by pi G R4, and then the final contribution FB3, then ER4. So I hope you here see my point in the comment that the torsion itself is not the main problem. Computing torsion, once you have the torsional moment, is very easy. But it is the effect of getting the torsional moment. So we had to go through some statics to be able to identify the torsional moment as being B multiplied by F. And then the effect that has on the whole structure, right? That the torsional beam rotates, therefore the handle will rotate, and we get a vertical deflection that will have to be superposed to the effect of the bending itself. So there will be an example in the problem session that will more illustrate this effect. Yes, and here we actually have 3 beams attached to each other, as we see here in the bottom. So that will be B28. So that is quite a tricky exercise. So please be very careful when you add the different contributions and think of the physical setup and how that actually affects what kind of contributions you have to the deflection. Then we have X14, which is a bit of a repetition exercise, and we have an extra exercise as well. So this concludes the lecture for today.